Switching gears to the campus, let's enable BFD using echo and non-echo techniques between our data center and core routers. Let's first explore a trivial BFD session between R7 and R3. Using the BFD interval command, we specify the minimum transmit and receive timers followed by the multiplier. These timers are quite complex, but to put it simply, they specify the minimum acceptable timer value. BFD timers do not have to match between peers. If one side wants 200 milliseconds and one side wants 300 milliseconds, the slower time of 300 milliseconds wins. 99% of the time, you should match these timers to avoid confusion, and that's what I've done today. As mentioned in the slides, BFD does not have a discovery mechanism and instead relies on protocols like EIGRP to form a neighborship first. Once that's done, we need to register EIGRP to BFD as a client. Let's check the EIGRP configuration to see how to do that. BFD is an interface level command, and I'm configuring it under AF interface default so that it applies to both of R7's core uplinks. R3 has a nearly identical configuration as well. Let's check the BFD neighborship using the command shown, which is very intuitive. We see one neighbor on this link, and it's R3. The state is up, and the LDRD represent the local and remote discriminators, which are dynamically generated values identifying each BFD speaker. Let's run the same command again, except with the details keyword appended to it. At the top, we see the same summary output as before. Then, BFD states that it is using the echo function. This means that R3 and R7 are sending IP packets towards one another, whereby the destination addresses are equal to themselves, but the MAC addresses target the remote device. This ensures the IP packet is looped back and processed by the original sender. BFD echoes are recommended whenever possible and are often processed in hardware, making them lightweight. Note that BFD echoes are enabled by default when you configure BFD at the interface level, as we just did. Also, we configured our transmit and receive intervals at 500 milliseconds. These other timers are a bit obscure, but to summarize, these represent the BFD control message timers. Sometimes these are called slow timers since they are only used to maintain the BFD session and are not often used for actual link detection. These are measured in microseconds, so 1 million microseconds is equal to 1 second. Towards the bottom, we see that EIGRP and Ceph are registered as BFD clients, indicating that if a BFD session fails, EIGRP will be notified so that it can reconverge around the failure. Let's explore a more nuanced configuration of BFD between R7 and R4. Under this interface, we've applied a custom BFD template. Let's explore that template in more detail. This template specifies the standard BFD parameters of minimum transmit and receive timers as well as a multiplier. That part isn't new. We've also enabled SHA-1 authentication using a keychain, which works like EIGRP authentication. Let's check the keychain to ensure it has at least one valid key. We see that key 1 is valid and it doesn't have any lifetimes associated with it, so it's good forever. Now, let's check the BFD neighbor details to ensure the session is up. Like last time, we see the summary details on top, and the BFD session is up with R4. This time, echoes are not in use. That's because if you use a BFD template, you must manually enable echoes using the echo command as shown in the callout. It's not enabled by default. Notice the slow timers are set to 500,000 microseconds or 500 milliseconds. Because we aren't using echoes on this peer, BFD relies on its control messages for both session maintenance and for link failure detection. That's not ideal, but it does work and it's better than nothing. We can see EIGRP is properly registered as a client and that SHA-1 authentication is enabled without issue. To test this, we need to be smart. We can't use the interface shutdown command because that will trigger an EIGRP notification to tear down the session. In my personal testbed, disconnecting a virtual link can cause weird issues, so I'd like to avoid that too. Instead, let's craft an ACL that drops BFD and EIGRP packets on ingress, causing the routers to believe a link failure has occurred. Remember that BFD control messages use UDP port 3784 and BFD echoes use UDP port 3785. We'll also drop EIGRP just so it doesn't rebuild a session after BFD fails. We'll drop all those packets and permit everything else. Using the snippet shown, I'll apply this to both BFD-enabled interfaces, which should cause failures within a few seconds. Upon cursory review, we see BFD detecting the failure quickly. Remember, smaller BFD timers mean faster failure detection, but adds load on your devices and links. If you're testing in a lab, you can use bigger values, but in production, use smaller values based on your business needs.